This is the second part of the video about continuity, and just to get started, I want to remind you of the definition of continuity at a point. So we say the function f is continuous at a point if the limit as x approaches the value a for the function f is the same as the function value at a. This includes these two ideas that the limit as x approaches a for this function exists, and f of a is defined. Right, so technically there are three properties that need to hold, but the third, the one I wrote first, actually incorporates the other two, that the limit as x approaches a for the function exists and the function value at a is defined. Right? And just a reminder about why we care about continuity when we're talking about limits. If a function is continuous at a, we can use direct substitution to evaluate the limit. So it tells us it's really easy to evaluate this limit. So, some properties of continuity, and these are going to look a lot like the properties of limits that we had in an earlier section. It says if b is a real number and f and g are functions that are continuous at x equals c, then all of these other combinations of functions are also continuous at that same point. So we can multiply the function that we know is continuous by a scalar, so we can double it, triple it, multiply it by -5, and that new function is also continuous at that point. We can add or subtract the two functions that are known to be continuous at the point, and we get another function that's continuous at that point. We can multiply the two functions, or we can divide them, and we can maintain that continuity. The only exception is if we end up creating a 0 in the denominator when we do the division, then the new function would not be continuous at that point. But as long as the denominator is not 0, then dividing the two functions will create a new continuous function. Using those combinations, we can conclude that all polynomial functions are continuous on their domains, all rational functions are continuous on their domains, radical functions are continuous on their domains, trig and exponential and logarithmic functions are all continuous on their domains. Right? So it's important to know how to figure out the domain of a function, but if you can do that, most of the time you can tell where the function is continuous. And then lastly, when we compose two continuous functions, then that composition is also continuous. So let's take a look at example 4 here. We have 3 different functions and we want to just figure out what are the intervals over which each function is continuous. So example 4a says f of x is the absolute value of x plus 3 over x plus 3. And we can think, well, I know the absolute value function itself is continuous everywhere, right? That's just a v shape. And the function x plus 3 is continuous everywhere. So their ratio will be continuous whenever the denominator is not 0. Right? So we can say this function is continuous on the interval from -infinity to infinity, and x plus 3 is also continuous on that same interval. So the quotient is continuous as long as the denominator is not 0. So as long as x plus 3 isn't 0, so f is continuous as long as x is not -3. So we could say on the interval from negative infinity to negative 3, union negative 3 to infinity. Those two intervals. All right, so the next one, f of x equals cosecant of pi x. This is a trig function, so it's continuous on its domain. So we need to just determine the domain. I'm going to rewrite it in terms of sine because for me that's more familiar. So we can see, okay, this is continuous as long as sine of pi x is not equal to 0. So if we think about the unit circle, and we think about the places where sine is 0 on each of those spots, right? So each of those are multiples of pi. So we don't want pi x to be a multiple of pi. So we can't have pi x equal to k pi. So these are the places where the sine value would be 0, any multiple of pi, and pi x is our input here. So it looks like if x is any integer, we're going to have a problem. We'll have a 0 of the denominator. So we would say f is continuous maybe for the set of all x's such that x is not an integer. And just a reminder, integers are negative. I'm going to start with -5, -4, -3, and 0 is included, 1, 2, 3, right? So whole numbers, negative whole numbers, and then 0. All right, then the last one in this example, we have f of x equals 4 over 5 minus e to the x. And again, we have combinations of just constant functions like 4 and exponential functions that are reflected and shifted up 5. So the numerator and denominator functions are both continuous for all real numbers because the domain for an exponential function is all real numbers. So f will be continuous because it's the ratio of two continuous functions as long as the denominator is 0. So we want 5 minus e to the x not equal to 0. So we want to figure out where 5 is equal to e to the x. And if we take the natural log of both sides, we'll have natural log of 5 equals natural log of e to the x. And remember, natural log of e to the x, that's just x. So we have a problem when x is natural log of 5. Right? So our conclusion is this function is continuous on the interval from negative infinity to natural log of 5, together with natural log of 5 to infinity, and we're excluding natural log of 5 on both of those. All right. Then moving on to example 5, now we're just looking for the x values, if there are any, at which the function is not continuous, and then we want to describe each discontinuity as either removable, jump, or infinite. So the first one, f of x is 1 over x to the 4th plus 3. This is a rational function, so it's continuous on its domain. And the domain includes all of the values that do not make the denominator 0. So x to the 4th plus 3, we don't want that to be 0. And what you want to remember is x to an even power like that will always be greater than or equal to 0. So x to the 4th plus 3 is always actually greater than 0. So the domain is all real numbers. So this function has no discontinuities. And the next one, we have f of x equals sine pi x over 3 plus e to the x minus 1. So we have a combination, a sum, of a trig function and an exponential function. Sine and cosine are going to have domain all real numbers. So we would say sine pi x over 3. That's just like sine of x, except it is horizontally, let's see, pi over 3 is slightly bigger than 1, so horizontally compressed slightly, but the domain would be all reals. So we would say that function has no discontinuity. And same with e to the x minus 1. That's just e to the x shifted 1 to the right, so that has no discontinuity. So this function has no discontinuities because the two individual functions have no discontinuity.
In example C, we have f of x equals x plus 2 over x squared plus x minus 2. So anytime we see a rational function like this, we know we would need to factor it. So x plus 2 over, that would be x plus 2 times x minus 1. And so we see we have repeated factors. And we are thinking, well, this is the same as 1 over x minus 1, except for when x is 1, this function would have I have that reversed, x is negative 2, where the numerator and the denominator are both 0. This will have a hole in the graph. So we can see that the denominator is 0 at two places, both at negative 2 and at 1. At negative 2, we have a hole in the graph, and at 1, since the denominator is 0 and the numerator is not, we know we'll have a vertical asymptote. So we have a vertical asymptote at x equals 1, and a hole in the graph at x equals negative 2. And those are the only discontinuities. So this one is that at x equals 1, we have an infinite discontinuity. And we have, removable discontinuity at x equals negative 2. And those are the only discontinuities for that function. Next up, we have a piecewise function. One of the branches is negative 2x, so a linear graph, and the other piece looks to be parabolic, x squared minus 4x plus 1. And the point that will be interesting to us will be x equals 2, right? Everywhere else we know that a linear function is continuous and a parabolic function is continuous, so it's just our question really right now is what's going on right at 2? So we could graph this, but we could also look at the limit as x approaches 2 from the left for this function, which would just be using the top branch, right, negative 2x, because that's what we would use for x's that are less than 2. So we can just do direct substitution, but use the correct branch, and that's going to be negative 2 times 2, so negative 4. So as we approach 2 from the left, we'll have negative 4, but as I approach 2 from the right, I will just do direct substitution with the other branch, and that will be, let's see, 2 squared minus 4 times 2 plus 1. So 4 minus 8 plus 1, negative 4 plus 1, looks like negative 3. So since the two sides are not approaching the same value, this is a jump discontinuity. At x equals 2. And that should be the only discontinuity because those two branches, like we said, both are continuous linear functions and parabolic functions. It's just when they meet up, we need to know, do they meet up at the same spot? And in this case, no, they do not. Then, before we move to the intermediate value function, we have one more, just the function f of x equals tangent of x. Right? And for me, it always helps me to think, okay, that's sine of x over cosine x, because I can always remember the general shape of the tangent graph. I know it has branches that do like that. I just need to remember where those discontinuities are. And I remember, well, they're all going to be vertical asymptotes, so vertical discontinuity, or excuse me, infinite discontinuities, but we just need to remember where they are. So I can see these will have a vertical asymptote when cosine of x equals 0, right? When the denominator is 0 and the numerator is not. And so I like to go back to my unit circle and think cosine of x, that's the x coordinate. So cosine of x is going to be 0 at these two spots in the unit circle. That's pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and so on. So vertical asymptotes will occur when x equals pi over 2 or any multiple of pi added on to that, right? Because anytime I rotate another half unit or half rotation, I'll have another place where the cosine is 0. So at x equals pi over 2 or any multiple, any integer multiple of pi added to that, we will have an infinite discontinuity. All right, then our last piece here is to talk about the intermediate value theorem. And this is what's called an existence theorem. And you'll see why in a second. So this says if f is continuous on a closed interval, remember closed means including the endpoints. So it's a connected graph and it connects up right up to the endpoints. And k is a number between the function values at the endpoints. Then there's at least one number, an x value. So this k is going to be a y value. And this c is going to be an x value because it's in the interval between a and b, such that f of c is k. So let's make a sketch. and set things up here the way they want. So we've got an interval from A to B, and these are x values. And our function is continuous on that interval. So I'm going to put f of A here and f of B here. And all I know is that I can get between those two without lifting my pencil. And they say k then is any number, so we pick some number between f of A and f of B. And we'll call that k. And I'm going to draw a line across here at the function value k. And what they're saying is there's at least one number c such that f of c is k. And what I can see from my graph is, well, for this sketch that I drew, the c value I'm looking for is right here for that choice of k. But let's make another choice of k. So if I choose a k that's a little bit lower, maybe right here, and I make my line across, well, this time I can see there are actually 3 values between A and B that give me that k value. So maybe I'd say, well, here's one of them, here's another, and then here's a third. Okay. So the theorem tells us there's at least one value of k, or excuse me, one value of c that will give us f of c equals k, but maybe there's more than one. But all we know for sure is there is at least one for any choice of k that's between those two function values for the two endpoints. So, like the note says, this theorem tells us that at least one c value exists, but it doesn't give us a method for finding that value of c. So it's just basically a useful theorem when we're trying to prove other theorems. But here's an example of how we might use this that is similar to what you might see in your homework. So it says, use the intermediate value theorem to show that this function x squared minus x plus 3 must take on the value 5 for at least one c on the interval between 0 and 3. So before we can use a theorem, we have to establish that we've met the criteria that it requires to be employed. So first we would have to verify that our function is continuous on the interval from 0 to 3, but this function is polynomial. So it's continuous on the whole real line, but certainly continuous on the interval from 0 to 3. Right? And that's all we need to get started with this theorem. But then we also need to say, okay, but then specifically, what y value are you talking about? We're talking about 5. So I need to know, what is f of 0? And f of 0 for this function would be 0 minus 0 plus 3. So f of 0 is 3. And f of 3 is 9 minus 3 plus 3. So that would be 9. And what we can see is 5, the y value they're talking about. We can say since 5 is between f of 0 and f of 3, there will be a c between 0 and 3 such that f of c is 5. So we know the theorem guarantees that such a value will exist because we said f of 0 is 3, f of 3 is 9, and I know this function is continuous, so I have to cross 5 along my way between getting from 0, 3 to 3, 9. I know I have to cross it somewhere, and now we're just asked to follow up, because this is a familiar function, find the value of c that actually is guaranteed by this theorem. So we just want to know what's the c value, so that c squared minus c plus 3 is going to be 5. And that's just a quadratic equation, so I can try to get a 0 and factor, and if it doesn't work, then I would use quadratic formula. But this will factor. And I get c equals 2 or c equals -1. So there are two c values that would give us f of c equals 5, but only one of them is between 0 and 3, and that's the one we're interested in right now. So we would choose c equals 2. If both of them were between 0 and 3, then we would choose both of them, but the one we're looking for this particular problem is c equals 2. Okay, then a couple true-false questions. The first one says, according to the intermediate value theorem, cosine of x minus sine of x minus x equals 2 has a solution over the interval -1 to 1. So if we're going to use the intermediate value theorem, we want to first check continuity and then check the function values at the endpoints and see whether this connection will give us a conclusion about something, a y value between the function values at the endpoints. So let's see, if we set this up as saying a function is equal to 2 between two x values, it looks like the function we're looking at is cosine of x minus sine x minus x, and that function is certainly continuous because it's just a combination of linear and sine and cosine functions, and each of those is continuous on the whole real line. So we can say f of x is continuous on the interval from -1 to 1. And then we want to check that 2, the function value we're interested in, is between f of -1 and f of 1. And so let's just check what f of 1 is and what f of -1 is. And those are not going to be familiar values, so I'm going to just grab a calculator. I don't want to graph these, I just want to know what the function values are. So I'm going to make sure I'm in radian mode. Yep, looks good. And then I want to do cosine of -1 minus sine of -1 minus -1. I get 2.38 roughly, and then f of 1, if I do cosine of 1 minus sine of 1 minus 1, I get -1.3 roughly. Right, and so I can see that since 2 is between f of -1 and f of 1, f of x equals to somewhere on the interval between -1 and 1. So again, I have this picture. I know that f of negative 1 is 2.38. And I know that f of 1 is negative 1.3. And I want to know, do I cross this line through y equals 2 somewhere in between? And because this is a continuous function, I don't know what the function looks like, but I know I'm going to have to cross that line at least once on that interval. So we would say this is true. And our justification for that conclusion is written there. And then the next one, if f is continuous and if f of a and f of b have opposite signs, then f of x equals 0 has exactly one solution on the interval from a to b. Right? And so we could make a little sketch. F of a and f of b have opposite signs. So maybe one is up here and one is down there, or the other way around. But if f is continuous, this has to be connected. And we said, oh, or maybe it's the other way around, right? Maybe f of b is up here and f of a is down here. But still, they have to be connected. We can at least conclude that f of x equals 0 has a solution, but the issue that we have with this statement is the exactly one. Maybe there are several, right? So maybe the function goes back and forth like that, right? So we would have to say false. It's almost something we can say, but the exactly one piece needs to change. So we could say the function will cross the x-axis at least once on the interval from a to b, but possibly several times. So hopefully that theorem you're starting to see how it works. We won't use it a lot, but it's just something that will come up again in explanations for other theorems. So hopefully it's making a little sense.